Aerial transportation using quadrotors with cable-suspended payloads hold exciting potential for applications in disaster response and logistics. However, their hybrid and underactuated dynamics pose significant challenges for control, perception, and state estimation. Perception-aware approaches can help guarantee that the payload remains within the camera's field of view, improving state estimation and allowing these systems to be deployed in real-world transportation tasks without relying on external motion tracking systems. We present a model predictive control framework, ES-HPC-MPC, that enforces exponential stability and perception safety under hybrid dynamics. Our MPC takes as input the reference trajectory and generates control commands that are sent to the body rate controller. Finally, the payload and quadrotor states are estimated using onboard sensors through VIO and Kalman filters. We experimentally validate our method through extensive real-world experiments using purely onboard sensors and computation. First, we subject the system to hybrid mode transitions during trajectory tracking. Next, we attempt to track dynamically infeasible trajectories. And finally, we demonstrate our method's ability to handle hybrid mode transitions during human interaction scenarios. In our first set of experiments, we show that our method can satisfy the perception constraints and enforce controller stability when the system is subjected to unexpected hybrid mode transitions. The value of the control barrier functions shown on the right validate that despite disturbances, the perception constraint is maintained throughout the trajectory. For a second set of experiments, we ask our method to track infeasible trajectories that are likely to cause the payload to exit the camera's field of view. Instead of reducing accelerations and velocities to satisfy the perception constraint, our method exploits the camera's asymmetric resolution and forces the system to yaw. Finally, we consider human payload interaction scenarios, where a user manipulates the payload, causing it to switch between the slack and taut states. Our proposed controller reacts to these disturbances and generates commands that guarantee satisfying payload visibility constraints throughout the entire experiment. The plot on the right shows that the control barrier function value remains positive during the experiment, demonstrating the effectiveness of our approach. Even though previous methods, such as HPA-MPC, introduced perception awareness for the system, their controllers lacked exponential convergence properties. In their side-by-side video comparison, we can observe that our method, shown on the left, results in a significantly more reactive controller compared to the baseline, shown on the right. Even when the human rapidly moves the payload, our controller maintains stability and consistently satisfies the perception constraints.